everyone, and welcome to section 5.2 lesson video. We're going to be learning about polynomials, linear factors, and zeros. Our objectives are that we can analyze the factored form of a polynomial, and we can also write a polynomial function from its zeros. So first of all, we need to talk about how finding the zeros of a polynomial function will help us factor the polynomial, graph the function, and solve the related polynomial equation. So before we kick it up a notch and actually talk about degrees bigger than 2, let's review a quadratic function and how to find the zeros. We did a lot of problems like this in chapter 4, so I just picked one random example. In this case, I have x squared plus 6x plus 8 equals 0. We want to factor that quadratic and find the zeros. So the method that we used to organize was the x method. So taking the last number and putting on top, taking the middle number, putting it on bottom. The two numbers that multiply to give you 8, but when you add them you get 6 are 2 and 4. And then from there, we wrote that in factored form, x plus 2, x plus 4. Because the product equals 0, that means one of the linear factors is equal to 0. So what we did next was we used the zero product property, which says that if you multiply two factors that equal 0, one of them must be equal to 0. So we're setting each linear factor equal to 0 and solving. So that means the zeros for this particular quadratic function are -2 and -4. We're going to be using these skills to solve for the solutions or the zeros of similar polynomial functions, but this time we're going to be changing up the degrees. In example 1, we need to determine the factored form of the polynomial x to the third minus 2x to the second minus 15x. What we want to do is write the polynomial as a product of factors and make sure that each factor cannot be factored any further. So when I take a look at this polynomial, I notice that each term has an x. So that means the GCF of this particular polynomial is x. Just like in the past, what we're going to do is take the GCF out, factor it, and put it in front. So now I have the x in front. Remember, when you're factoring out a GCF, you're essentially just dividing each of the terms by that GCF. So you're thinking to yourself, what do you have to multiply x by to get x to the third? Well, that's x squared. What do you have to multiply x by to get -2x squared? That would be -2x. And what do you have to multiply x by to get -15x? That would be -15. So from there, we can just factor what's in the parentheses because now we just have a quadratic expression. So I'm going to be using the x method to factor what's inside the parentheses. So I made myself an x right here. I have -15 on top and -2 on bottom, and we need to figure out what numbers multiply to give you -15, but when you add them they give you -2. Hopefully you're thinking to yourself, -5 and +3 work. So from there I'm going to write directly below my factored form. I still have the GCF of x in front, and then taking the two numbers inside my x, I have x minus 5 and x plus 3. And that would be the factored form of the original polynomial. I'd like to briefly show you how to check your answer. So we have the factored form here. I'm going to keep the GCF in front for a moment, and I'm going to be using the FOIL process to multiply these two binomials. So we get x squared plus 3x minus 5x minus 15. And of course we want to combine like terms inside the parentheses, so we have x squared minus 2x minus 15, and then distribute the GCF x to each term inside the parentheses. So that means we get x to the third minus 2x squared minus 15x, which was the original polynomial. So that ensures that we did the right thing. This key concept box here helps us organize some equivalent statements regarding roots, zeros, and x-intercepts. So say, for example, we have a real number b. If we said that x minus b is a linear factor of the polynomial function, then the b would be a 0. It's also called a root or a solution, and it's also called an x-intercept of the graph. So now let's make it more real and actually do an example at right. So my example equation is p of x equals -x to the third plus 2x plus 4. We're going to let x equal 2. So that means when I substitute in 2 for x, I get a y value or an output value of 0. So therefore, I can conclude that x minus 2 is a factor of the function. This means that 2 is a zero of the function. It also means that 2 is a solution to the equation when it's set equal to 0. And lastly, the point 2 comma 0 is an intercept, an x-intercept of the graph. So one more time to reiterate what I just said, x minus 2 is a factor of the polynomial function that we were given. That means 2 is a 0, which also means that when you set the polynomial function equal to 0, 2 is a solution of that equation. And lastly, 2 comma 0 is one of the x-intercepts of the graph. In example 2, we need to determine what the zeros are of the function y equals the quantity x plus 2 times the quantity x minus 1 times the quantity x minus 3. Once we find those zeros, we can graph the function. The nice thing about this problem is that the polynomial is already in factored form, so we don't need to go through the factoring process. So the first thing we want to do is use the zero product property to find the zeros. So that means set each of the factors equal to 0 and solve. So once I set each of the factors equal to 0, I just need to do one step to find the zeros, which means the opposite. So if I'm having x plus 2 equals 0, that means my first 0 is at negative 2, my second 0 is going to be at positive 1, and my third 0 is going to be at positive 3. So that means our zeros of the function are negative 2, positive 1, and 3. Now that we know the zeros, we want to figure out a couple points for the x values between the zeros to figure out what's happening between the zeros, if it's going to be above or below the axis. So I chose x values of negative 1, 0, and 2. So now take a moment to write these three x values down and plug them in to the given function to figure out what the y values are. When substituting in negative 1 for the function, I get a y value of 8. So that means one coordinate point between a couple of the zeros is negative 1 comma 8. When substituting in 0 for the function, I get a y value of 6. So my next coordinate point would be 0 comma 6. And then when substituting in positive 2, I get a y value of negative 4. So the last coordinate point is 2 comma negative 4. So now let's take a moment to plot those coordinate points that we just found as well as the three zeros that we found above. Now that I have those points plotted, let's talk about the end behavior of this function. I know that this function is a cubic function because I have three linear factors being multiplied. So that means when I multiply all those out, I'm going to get x to the third in the beginning. And you also notice that there are no coefficients besides 1 in front of those x's. So that means my leading coefficient is a equals 1, positive 1. So using the knowledge that we acquired in the previous lesson video 5.1, the end behavior would be down on the left and up on the right. Lastly, we just need to connect our points and draw arrows based off of our end behavior. Now, you probably are thinking to yourself, well, this isn't perfect because we don't know every other coordinate point on this cubic function. You're correct about that. This is kind of like a rough sketch, but we will be, of course, using our calculator in the near future to ensure that we are graphing as accurately as possible. The factor theorem describes the relationship between the linear factors of a polynomial and the zeros of a polynomial. So the factor theorem says the expression x minus a is a factor of a polynomial if and only if the value a is a zero of the related polynomial function. I'm hoping that you remember if and only if statements from geometry last year, but let me remind you what they mean. If and only if means that the reverse of the statement is also true. So the statement says if x minus a is a factor, then x equals a is a zero. The vice versa would be if x equals a is a zero, then x minus a is a factor. So that's what if and only if means. In example 3, we are asked to write a cubic polynomial function in standard form with zeros negative 2, positive 2, and 3. So because I know these are the zeros, what I want to do is write the factored form using the factor theorem above. So by the factor theorem, if negative 2 is a 0, that means x minus negative 2 is a factor. So to simplify x minus negative 2, that would be x plus 2. If positive 2 is a 0, then x minus 2 is a factor. And lastly, if positive 3 is a 0, then x minus 3 is a factor. So there's the factored form. From there, we want to multiply out to get our polynomial in standard form. I just took a moment and multiplied the factors x minus 2 and x minus 3 using the FOIL process. The shortcut is you can multiply the negative 2 and the negative 3 to get positive 6, and you can add those two numbers to get the middle number of negative 5. From there, I'm going to be distributing the x plus 2 to that expression. So to make the distributive property easier, I broke apart the x plus 2 so that we can separately distribute those terms. So when I distribute x to the expression x squared minus 5x plus 6, I get x to the third minus 5x squared plus 6x. And then when I multiply or distribute the 2 to that expression, I get 2x squared minus 10x plus 12. From there, we want to combine like terms to get it in standard form. When doing so, I get the function f of x equals x to the third minus 3x squared minus 4x plus 12. This cubic polynomial has zeros, -2, +2, and 3. Part B is asking us to determine what the quartic polynomial function is in standard form with the zeros -2, -2, +2, and 3. So the process is very similar to Part A. So I write out the zeros, and then from there I'm writing out the linear factors. So I have x plus 2 times x plus 2 times x minus 2 times x minus 3. I just changed the name of the function to g of x to easily differentiate between part A and part B, so you can do the same. When you multiply out all those factors, you get the function g of x equals x to the fourth minus x to the third minus 10x squared plus 4x plus 24. And this function has the zeros that we were given in the beginning, -2, -2, +2, and +3. Part C is asking us to graph both functions and discuss how the graphs differ and how they are similar. We're going to be using our graphing calculator to assist us in this process. So have out your graphing calculator and feel free to pause here to input both of the equations, f of x and g of x. So now that you have your equations inputted, make sure you just have y1 highlighted so that you're not graphing both at the same time. So press trace and let's see what it looks like. Right now my window is too small, so I'm going to fix it. Feel free to have your window match mine. I have -10, +10 for the x, min and max, and then the scale for x I just go by ones, and then for the y min and the y max respectively -10 and +20, and for the y scale I have +5 to help us see it more clearly. So now press trace and we can see the shape of this graph. Now go back to your y equals and unselect the y1 and now go over to y2 and select it. And let's go to trace. And it looks like I will need to expand my window for the y direction. So let's try +30 here. Okay, so that helps us see the end behavior and the turning points and all that. So I'm going to take a screenshot of this and then let's talk about it. Taking a look at both of these graphs, I noticed that they have x-intercepts at -2, +2, and 3. So that is the similarity that they share. They do have several differences, so now let's discuss those. The first difference is that of the end behavior. So you can see in the graph that the cubic function has a down and up end behavior. The quartic function has an up and up end behavior. The second difference is the amount of turning points. The cubic function has 2 turning points located here and here, and the cubic or quartic function has 3 turning points located at this point, and this point. And the last difference is the cubic function crosses at the x-axis at x equals -2 at this point right here. But for the quartic function, it touches the x-axis at that point, but it does not cross it. And we will actually be discussing that difference in just a moment. Using the factored form of the functions that we just worked with in example 3, we have f of x equals x plus 2 times x minus 2 times x minus 3. And g of x equals x plus 2 quantity squared, because we had that listed twice, times x minus 2 times x minus 3. This -2 is called a multiple zero, and the reason why is because the factor x plus 2 is listed twice. So -2 is a zero of multiplicity 2, and the reason why is because we listed that factor twice. The key concept box generalizes this idea. So if A is a zero of multiplicity n, aka A is a zero and you see that n times, where n is a real number, in the polynomial function y equals p of x, then the behavior of the graph at that x-intercept A will be close to linear if n, the multiplicity n, is equal to 1, close to quadratic if n equals 2, close to cubic if n equals 3, and so on. So what that means is, if a is a zero of even multiplicity, aka you see that zero an even number of times, then that means the graph is going to touch the x-axis at that x-coordinate, that x-intercept a, and it's going to turn around. So that confirms what we did above, right here. For this quartic function, we had the graph hitting the x-axis at the x-coordinate of -2 and then bouncing back. And that's because we saw that zero twice. The other possibility is if the a is a zero of odd multiplicity. If that's the case, then the graph of the function is going to cross the x-axis at that point a. So going back to the example that we just did above, all of the other zeros were only listed once. So that's why the functions are going through that point only once. In example 4, we're given the function f of x equals x to the fourth minus 2x to the third minus x squared. We need to determine the zeros, what the multiplicities are, and how the graph behaves at these zeros. So what we want to do is factor the polynomial that we're given, and then find the number of times each linear factor appears. So when I'm taking a look at this function, I notice that there is a GCF of x squared. So as always, we're going to factor the GCF out and put it in front. So when I factor out x squared, I get a remaining polynomial function of x squared minus 2x minus 8. So that's the expression inside the parentheses. From there, it's a quadratic that we learned how to factor in the previous chapter. So when you factor that, I'll do the work on the side real quick, -8 and -2, the numbers that work are -4 and 2. So we have x squared still in front, x minus 4, and x plus 2. So that would be the factored form of the given polynomial. We can rewrite the GCF x squared as the quantity x minus 0 squared to easily show what the 0 would be here. The number 0 is the 0 of multiplicity 2 because we see that twice. So you can see in the graph at the origin, the graph or the curve is resembling a parabola. When setting x minus 4 equal to 0, I get 4, and when setting x plus 2 equal to 0, I get -2. The numbers 4 and -2 are zeros of multiplicity 1 because they occur only once. And you can see at the graph at those two zeros, the line or the curve resembles a linear function because the curve is just going through the x-axis once there. So like we just discussed, the graph resembles a parabola at the x-intercept 0 and looks close to linear at the x-intercepts -2 and +4. If the graph of a polynomial function has several turning points, the function can have a relative minimum and a relative maximum. A relative minimum is the value of the function at a down to up turning point. So you can see in the graph below, the cubic function is going down to up in the first part. So that point at the lowest point between those two directions, that is called a relative minimum. The vice versa, or the opposite of that, would be a relative max. And that is the value of the function at an up to down turning point. So you can see at this next point, the left side of that curve is going up or increasing, and the right side of that curve is going down or decreasing. So that point, the turning point, is called a relative max. You may be wondering what the difference is between a relative max/min and a max or min of a parabola at its vertex. A relative max is the greatest y value in the neighborhood of its x value, versus the maximum at the vertex of a parabola is the greatest y value for all x values. So it is possible in a graph of a polynomial function to have several relative max or mins. It just depends on what x values we're talking about. So I hope that helps differentiate the two. In example 5, we are given the function f of x equals x to the third plus 3x squared minus 24x. We need to determine what the relative max and min are, and we're going to be using the graphing calculator to assist us in this process. So you can turn your graphing calculator on and input the given function. Before pressing trace, I suggest changing your window to match mine so that you can have the relative max and min show up on your graph. And notice that I changed the scale to go up by tens so that we can fit it in. Okay, now go to trace. And we are going to be using the max and min features and the second calc button. So let's go to min first. And you can do that process right now, so pause the video and do each of those. We did go over that process last chapter. To speed up this process, I have the graphs shown here as well as the tables. And you can see in the first graph we have the max at -4, 80, so that means the relative max is 80 at x equals -4. You can also see this in the table. The relative min is located at the coordinate point 2, -28, so that means the relative min is -28 at x equals 2. So that is the process that we will follow for finding relative max and mins. In example 6, we're given a real-life scenario where we're going to be using this knowledge. It says the design of a digital box camera maximizes the volume while keeping the sum of the dimensions at 6 inches. If the length must be 1.5 times the height, what should each dimension be? So the first step is to define our variable, and since talking about the height, we're going to be using x for the height of the camera. Now we want to determine expressions for the length and the width. It was told in the description that the length must be 1.5 times the height, so that's where I got my expression length equals 1.5 times x. It also told us that the sum of the dimensions of the length, the width, and the height needs to be 6. So if I know that my height is x and my length is 1.5x, I just need to subtract both of those from 6 to get my width. That means my expression for my width is 6 minus 2.5x. Now we're going to be using the volume formula, which is equal to length times width times height, and I'm substituting in each of the expressions involving x. When I multiply those expressions, I get the equation v equals -3.75 x to the third plus 9x squared. When I graph this polynomial in my graphing calculator, I used the maximum feature and found out that the maximum coordinate is approximately 1.6, 7.68. That means the maximum volume of this camera box is 7.68 cubic inches, and that occurs when the height is 1.6 inches. Now that we know the height is 1.6 inches, we can easily substitute in 1.6 for the expressions that we found above. So I find out that the length is 2.4 inches and the width is 2 inches. If we were to add all those dimensions together, we would get 6 inches, so it does satisfy the requirements. Here's our lesson check problems for section 5.2. Make sure you write them down, complete them, and let me know if you have any questions the next time we meet.